Welcome to This Explainer. So if you've ever broken a bone or, even just seen someone clunking around in a cast, you probably have a really distinct image in your head of how bone healing works. You lock the bone in place, don't move a muscle, and just let time do the rest, right? Well, today we're going to uncover a totally fascinating and honestly deeply counterintuitive truth about orthopedics. Sometimes, to heal perfectly, a broken bone actually needs a specific, precisely engineered amount of movement. We're talking about the biomechanical modulation of stability in osteosynthesis, or as the sources often describe it, the Goldilocks principle of bone healing.
So I want to pose this question right off the bat. Does a broken bone actually need to be perfectly rigidly still to heal? For decades, absolute immobilization was considered the holy grail of fracture treatment. If a bone didn't heal right, the assumption was always just, well, it wasn't held still enough. But as we're about to see, human biology is way more complex and frankly, a lot more interesting than just locking a broken bone in a vise.
Here's our roadmap for this explainer. First, we'll look at the evolution of osteosynthesis. Then, Perrin's theory of strain. From there, we'll dive into absolute stability, followed by relative stability. Fifth is the power of micromotion. And finally, we'll wrap up with the surgeon as engineer.
Okay, Section 1. The evolution of osteosynthesis. Before the 1950s, the standard of care was almost entirely what we call conservative treatment. Championed by Lawrence Bowler, this basically meant reducing fractures and stabilizing them externally with splints, heavy plaster casts, and traction. But here is where the history gets really cool. On March 1, 1950, a young Swiss surgeon named Maurice Müller visited Robert Danis in Brussels. Danis had actually been quietly experimenting with surgical treatments for 25 years, literally using plates and screws directly on the bone. This single day totally revolutionized Müller's thinking. He took Danis's concepts, refined them, and in 1958, Müller and his colleagues founded the AO Foundation in Switzerland. That group essentially birthed modern operative fracture treatment, permanently shifting the whole medical world from passive external casting to active internal fixation.
Moving on to Section 2. Perrin's theory of strain.
To really wrap your head around how modern trauma surgeons fix bones, you have to understand this core concept called strain. In biomechanics, our sources define strain as relative deformation. Mathematically, it's actually pretty simple. It's just the change in length of the fracture gap, when a load or force is applied, like stepping on your leg, divided by the initial length of that gap. It gives us a simple percentage. And believe it or not, this one simple ratio determines absolutely everything about whether a bone will heal successfully or if the surgery will completely fail.
And this brilliantly illustrates the central paradox of bone healing. Look at the numbers. If you have a tiny fracture gap of just 1 millimeter, and you allow just half a millimeter of movement, that creates a massive 50% strain. The delicate tissue trying to bridge that tiny gap will literally be torn apart by that movement. You'll end up with fibrous scar tissue instead of bone, leading to the dreaded non-union. But if you have a wide, multi-fragmentary gap of, say, 20 millimeters, that exact same half millimeter of movement is distributed across a much wider space. The strain drops down to a totally safe, biologically optimal 2.5%. It's wild, right? The exact same amount of physical movement is a complete disaster in a small gap, but perfectly healthy and stimulatory in a large one.
Which leads us to Sections 3 and 4, absolute versus relative stability.
Looking at the data, it's pretty amazing to compare these two distinct environments that surgeons have to choose between. In absolute stability, the target is reducing strain to less than 2%. This practically eliminates all movement, resulting in what's called primary healing, where the bone remodels directly across the fracture without creating any visible callus. On the flip side, relative stability intentionally allows a controlled strain of between 2 and 10%. This stimulates secondary healing, which is where the body forms a visible hard bony callus around the fracture to stabilize it naturally. These are two completely different biological responses, and they are dictated entirely by the mechanical limits set by the surgeon.
So, let's look at the actual hardware to see how this plays out in the real world. On the left, we've got absolute stability tools, like lag screws and compression plates. Their whole job is to forcefully compress the bone ends together, utterly eliminating the gap so strain stays securely under that strict 2% threshold. On the right, though, for wider, multi-fragmentary gaps where absolute stability is just impossible, surgeons use bridging techniques. These intentionally distribute deformation across a wider area, achieving relative stability and encouraging a callus to form.
And this brings us to a really fundamental rule, famously stated in our source material as menos movimiento que el tejido puede tolerar, or ensuring less movement than the tissue can tolerate. This is absolutely critical. If you are attempting absolute stability because the fracture gap is small, you literally must eliminate micromovement. Any excessive strain over 2% here is going to prevent direct osteonal remodeling, and you'll get fibrous scar tissue instead of bone. Basically, if you accept a gap while trying to be absolute, you're accepting failure.
All right, Section 5, the power of micromotion.
Now, I want you to notice this staggering number, 20%. Back in 1989 and 1991, clinical trials confirmed something that completely bucked historical intuition. Intentional, carefully controlled micromotion at the fracture site actually reduces healing time by 20%. Allowing the bone to move just a little bit in the exact right direction serves as a massive biological signal that kicks the body's repair mechanisms into overdrive. This realization stems from some pioneering work by researchers like Goodship and Kinwright in the 1980s. You can see an external fixator used in their research right here. By deliberately applying controlled axial micromotion, which basically means slight intentional compression and distraction directly along the vertical length of the bone, they proved that this specific mechanical stimulus vigorously stimulates callus development and dramatically increases the overall stiffness of the healing bone.
And the science gets even more granular, which I found just incredible when reviewing this data. In 1999, researcher Lutz Klias and his team published a landmark study showing that the specific magnitudes of local stress and strain literally predict how tissue differentiates at the cellular level. If strain is under 5% and hydrostatic pressure is low, you get intramembranous bone. Add a little compressive pressure and bump that strain up to between 5 and 15%, you get cartilage and endochondral ossification. Anything higher than that, the cells default to fibrous connective tissue. The cells are essentially listening to the mechanical environment to decide what kind of tissue they need to become. Mind-blowing, right?
Finally, Section 6, the surgeon as engineer.
So, the really crucial takeaway here is that a modern trauma surgeon doesn't directly control strain. They control the structural variables that create the strain. They follow a literal engineering workflow in the operating room. First, they assess the functional gap length of the fracture. Second, they estimate the amount of physical load and movement the patient's body is going to put on that bone. Third, they calculate the expected strain. And finally, they select and install a construct, carefully choosing plate length, screw position, and material rigidity to dial in either a perfect absolute or a perfect relative stability environment.
Which brings us to the ultimate philosophy of modern fracture care. The success of osteosynthesis depends not on the implant, but on the mechanical environment we generate. A titanium plate or a steel screw doesn't actually heal the bone. The patient's underlying biology heals the bone. The hardware is simply an engineering tool used to meticulously modulate the biomechanical environment, giving those biological processes the exact strain conditions they desperately need to thrive.
So I'll leave you with this final thought. The next time you see someone with a cast, or maybe you look at an X-ray of surgical plates and screws, don't just see chunks of metal and plaster. Ask yourself, what kind of mechanical environment is that surgeon actually building in there? Are they locking it down tightly for an absolute, zero-strain primary healing? Or are they carefully allowing the absolute perfect amount of micromotion to summon a robust biological callus? The line between broken and healed isn't just biology, it's pure, elegant biomechanics. Thanks for joining me on this explainer, and keep questioning the world around you.